Yep, welcome back everybody. I'll be chairing this last session of the workshop. It's my pleasure to introduce Andy Weiner from Purdue University, who will be speaking to us about frequency bin quantum photonics. Please.
Good, thank you. Thank you for those who are still here. So again, I'll talk about frequency bin quantum photonics. Another word we like for this are biphoton frequency combs. But basically, one idea is illustrated here where, for example, if we come with CW light into a microresonator, through spontaneous four-wave mixing, we can get signal-idler pairs that are emitted in multiple different sort of quasi-discrete frequency positions, and we're interested in entanglement among many different degrees of freedom, as well as manipulation. So I listed a number of the students, either recent or current or recent, who participated in this. My colleague, Professor Minghao Chi, is a collaborator, and we have very close collaboration with folks at Oak Ridge National Lab, both Pavel Lugovsky, who spoke here, and Joe Lukens, who will speak in a little bit in this sort of area as well. So, very briefly, the type of sources. I think I don't have to spend too long about this in this particular forum, but so we're interested in either parametric down conversion or spontaneous four-wave mixing. As you know, in parametric down conversion, we get signal and idler pairs that have tightly correlated frequencies for the signal and the idler, even though the individual frequencies are over a broad band, sort of spanning the C-band in our particular experiments. Also with nice time correlations. Now, this is usually a continuous spectrum, but if we're interested in discrete spectra, we'll be interested in experiments where we use a periodic spectral filter to give frequency bins. As I mentioned, the microring resonators naturally emit photon pairs here through spontaneous four-wave mixing in discrete frequency bins corresponding to the separation of the resonances. And so in a very simple sense, we may think of these bins as being some kind of a quantum analog of WDM. It'll be more than that because we're interested in coherent superpositions of frequencies. But so this is what we'll talk about. A little bit about motivation. So, frequencies are a very robust degree of freedom. Certainly we know that from the way they are used in being transmitted over optical fibers. Yet they're somehow maybe relatively underutilized or unexplored until recently, for encoding quantum information. There's a natural potential, as I mentioned, for high dimensionality, so we can be interested particularly in processing with qubits as opposed to qubits, with the possibility of more than one qubit encoded per photon. Practically, classically, we know very well how to perform routing based on optical frequency. That's the basis for telecom devices like wavelength selective switches. That kind of capability will, as you see, be useful in the sort of quantum experiments we do as well. As in WDM, we have parallelism, and so we can be interested in manipulation of quantum states of light in parallel across the frequency domain. We're going to be talking, at least for part of the work, about chip-scale microresonator sources, which sort of brings a potential for photonic integration. And finally, in addition to frequency, we can combine with other photonic degrees of freedom. I'll talk about time-frequency hyperentanglement and some work on deterministic two-qubit dates, two-qubit gates based on such hyperentanglement. And because both time and frequency have been carried in a single spatial mode, you can start to think about maybe in the future combining that with the spatial degrees of freedom that are already heavily explored in integrated photonics. So I'll give a little bit more of an outline of frequency bin quantum photonics. Probably the biggest part of my talk will be about how to test or verify frequency bin entanglement, because usually we think of frequencies as not interfering well, giving fast time domain patterns that are hard to measure. So we'll talk about verifying frequency bin entanglement and some simple, maybe quote applications. I'll talk also about time frequency hyperentanglement, and as I mentioned, This bullet I had a hard time pronouncing, deterministic two qubit gates in a single photon. And then very briefly, I'll talk a little bit about integration potential and finish the talk. So there's been a great deal of interest in classical optical frequency combs for going on to 20 years now. In the last 10 years, there's been activities in CW pumping of microresonators and through nonlinear Kerr effects, making classical frequency combs. We're one of many groups who's been very kind of interested in that. In the quantum regime, we're talking about something different, but this is something that's really started to catch on just in the last couple of years. And so two examples of nice papers here. One is from the group of Jeff Shapiro and Franco Wong and colleagues, have a parametric down convergence source that is periodically filtered by a etalon. And what they're doing, for example, are Hong-O-Mandel experiments. This is the delay axis. And they're showing instead of getting just a single Hong-O-Mandel dip, they get periodic revivals having to do with the space inversely with respect to frequency bins. Another experiment by the group of Roberto Morandati and colleagues at INRS in Canada published this paper a little over 2 years ago where they're pumping, see if there's a picture here, but these are basically on-chip microresonators with short pulse sequences, pulse pairs, and showing that both photons could get emitted in sort of signal and idler frequency bins, but also looking at some time domain and entanglement notions. So these are both very interesting, but another observation I'll make is actually neither of these actually explore frequency bin entanglement or coherent superpositions across frequencies. So that's kind of a direction we were interested in. And so let me get into that. Our first experiments pumping micro-ring resonators, in both cases, you come in with a CW single frequency pump, bring it into resonance, you observe the output. These are two different microresonators on a silicon nitride on oxide platform. Depending, this is a smaller one, this is a larger one. They look the same as portrayed here. And so that controls the free spectral range of the frequency bands. So if you look here, for example, and look at just an OSA spectrum, you have a strong pump line. It's in band, it's already attenuated probably by about 60-ish dB or so. Okay, but then you see these signal idler sidebands, and you can see maybe half a dozen lines. And see there's spontaneous four-wave mixing. If you do a joint spectral intensity, and so using pulse shapers, we can programmably pick different frequency bins. And so if we look at signals versus idlers, we see coincidence counts that have the strong diagonal character. So that's when the frequencies are anti-correlated and preserve energy, and very little off-diagonal. You can kind of look at the coincidence peaks on diagonal. They're kind of around a nanosecond long, corresponding to a few hundred megahertz resonant bandwidths. And you can see pretty good coincident accidental ratio when you look for kind of an off-diagonal pair. And then in this ring, which has instead of 380 gigahertz space resonances, 50 gigahertz space resonances, we can fit more bins within sort of the emission bandwidth. So here we can see a very strong high dimensionality. We can measure out to about 40 correlated signal and idler photon bins. So if you could really coherently use all of this, you might have more than 5 qubits in a single photon. So that really motivates the potential for going to dimensionality higher than 2. Another early experiment that we did here was simply taking the signal and idlers that were generated, separating them, taking the high frequency part and the low frequency part, and programmably routing them to different fibers and interacting with dispersion. So dispersion is a good tool to manipulate a frequency and stretch it in time. And so if we start with a sort of an undispersed coincidence peak between signal and idler, this is really 4 lines that overlapped with each other, but they're all kind of blurred together into a single peak. But with, and by the way, they're blurred together because any time structure that should be there is on a very fast time scale, much too fast to detect directly, giving the timing jitter of single photon detectors. Okay, but with dispersion, we can put, say, just the signal beams to a chirp fiber Bragg grating that gives sort of, I think, 2 nanoseconds dispersion per nanometer. We can spread the 4 signal idler coincidence peaks out. We can map them into multiple nanoseconds so you can visualize it. We can do nice experiments where we put the chirp fiber Bragg grating in the other arm, not in the first. We can disperse them and sort of with the opposite symmetry. And if you have equal and opposite dispersion in both arms, essentially it kind of recombines all these peaks into one. And so we can view this as both sort of a frequency to time mapping capability or really an example using these microring resonators of non-local dispersion compensation, which of course is a sort of a foundational concept in time energy entanglement dating back to, Franson's work around 1990. Okay, but that work also didn't show anything really about entanglement. It showed frequency correlations. What's the difference? Well, the difference is coherent superpositions, which we're always interested in our quantum. And so, let's think of the frequency of entanglement like this. If we look at the spectra, we have some strong pump that we're going to have to block out if we're doing spontaneous Fourier mixing. And then we can have these signal idler frequency bins. Now, each of these has some line width, which is kind of 100 megahertz scale, but they're spaced by tens of gigahertz or more. So, kind of quasi-discrete. And these solid arrows connecting them are showing the frequency correlations that are measured whenever you measure joint spectral intensity. Okay? The dashed lines here are suggesting a phase coherence between these different biphoton pairs. And it's that phase coherence that really is at the heart of frequency bin entanglement. So, if we look at the math, for example, we, say we have a coherent superposition of signals and idlers that are different pairs, and coherent means that those coefficients have a phase that really means something and is stable, and the relative phases, in fact, would influence the time correlation function and give you some structure, which is already mentioned, is sort of too fast to measure directly. So the question then is how can we measure the entanglement, avoiding the problem with frequencies beating with each other so fast that we can't directly measure it. Okay, so the tools are going to be 2 things, pulse shapers, which I've mentioned briefly, and phase modulators. And so pulse shapers, this is one of my pictures from some years ago, was a technology that I was involved in developing when I was a few years younger for essentially making arbitrary femtosecond type optical waveforms, classical waveforms, and is based on using frequency dispersive elements like grating to take different frequency elements in a single beam, spreading them out spatially, introducing modulator arrays, or usually call them spatial light modulators, to control amplitude and phase, and recombining into sort of a coherent beam. Okay, for our purposes here, this is just going to be a programmable amplitude and phase programmable device, and it also in some of the modern implementations, this is a commercial implementation from Finisar that's usually called a wave shaper. These grew out of wavelength selective switches, which themselves are generalized in pulse shaping to allow also routing of different frequencies to different output, spatial modes. So we can also kind of programmably route frequencies. Okay? The first use of these pulse shapers in the quantum world, not in the classical world, was by Jeroen Silberberg's group now about 13 or 14 years ago, and they really showed how you could do this coherent filtering on a biphoton spectrum and manipulate picosecond or sub-picosecond structures and time correlation functions, which was measured by some frequency generation, sort of a quantum analog of classical intensity autocorrelation techniques. But that works, but is low efficiency and only allows local measurements, so we're interested in something else here. So we'll be using these pulse shapers. I think phase modulators are well known, but those are going to allow us to mix frequencies. And here I just highlight this first experiment that I know of kind of in this business by Steve Harris's group that used periodic phase modulation of signals and idlers to manipulate the strong frequency peaks between them into multi-peaks or to sort of recombine them into a single peak. So we're going to be using a periodic temporal phase to mix frequencies, and we're also going to control spectral phase with pulse shapers. So the basic scheme will look like this. I'll go into more detail on a slide in just a moment. But the idea, we're going to start with our biphoton frequency comb. We're going to use a first pulse shaper to select a subset of the signal and idler lines. okay, and to also put on programmable phases on them as we need to make quantum interference, two-photon interference experiments. We're going to go into a telecom phase modulator driven by an RF frequency, which will be in the tens of gigahertz regime, that produces sidebands. The right frequency brings sidebands together, so we overlap contributions from different signal and idler lines. We'll use a second pole shaper in a very simple way, just to sort of select some of the overlap sidebands, and then to separate or route them to two different signal photon detectors and do coincidence detection. Okay, so the phase modulator acts as a frequency mixer. It helps us make coherent superpositions of frequencies at a single frequency location. And what we'll be doing here is somehow very analogous to the use wave plates and polarizers used to mix polarization states to measure polarization entanglement, or also to sort of time bin entanglement where people use delay imbalanced interferometers. In some sense, we're doing a very analogous thing, but learning how to do it with discrete frequency bins. Okay, now interesting duality. What I'm going to be talking about mostly in this talk is on the top here, using pole shapers, phase modulators, pole shapers in this order for doing frequency bin entanglement characterization. Okay. Now, and in this technique, I'll be reporting our experiments here at Purdue. It turns out independently around the same time, Roberto Morandotti's group came up and demonstrated a very similar technique. Okay. Another idea is if you want to do manipulation of quantum states, or essentially gates. Joe Lukens and Pavel Lugovsky put forward an idea that you could do that with actually the same components, but using the EOMs and the pole shapers sort of in the converse way. And so, since their proposal, we've enjoyed a very nice collaboration with their group, and some of those experiments will be described by Joe just a little bit later this late afternoon. Okay, so let's go back to proving frequency bin entanglement. I already sort of showed this picture. Let's talk about it in a little more detail. So we're going to start with the biphoton frequency comb with some signals and idlers. We'll put on different phases on either the idler, the signal, or both. Really, it's the joint phase, signal plus idler phase, that matters. Okay, and what we're going to do is we're going to select out either out of the many, 2 or 3 of the signals and idlers. Okay, then we're going to phase modulate at a frequency which is exactly half of the frequency bin spacing. So we'll generate these sort of green lines here, which are the mixture of 2 or more sort of parent signal or idler frequency bins. Okay, so that's where we're going to get some coherent interference. We'll use a second pole shaper to grab sort of particular signal and signal idler and route them for coincidence detection. And then we'll look at the coincidences as we adjust these phase functions to kind of make our two-photon interference curves. Okay, so and we'll be doing experiments on kind of both of these things, either the silicon nitride microring resonators that directly put its light in frequency bins, or in parametric down conversion in Piplin waveguides that give continuous spectra, but followed by basically carving frequency bins with pole shapers. So it's sort of the scales here, I'll talk typically about 50 gigahertz separation for the microrings, sort of 100 megahertz line widths, give you sort of a nanosecond, a few nanosecond correlation times. With the SPDC, the pole shapers give us about 10 gigahertz resolution, so we'll have wider frequency bins, and we'll typically separate them sort of 36 gigahertz is a number that we like. So these are 2 sources that you'll see here. Okay. So next thing we have to do is, so we drive the RF and we want to bring some sine bands on top of each other. And so it turns out this is kind of a little bit hard because we know we have a 50 gigahertz frequency bin spacing. We don't know exactly. And we have, it's quantum, it's kind of low count level. So we had to learn how to kind of tune the RF frequency and bias the phases in such a way that we should get a strong dip in coincidence when we got RF, sort of the right RF frequencies. So this is kind of a cartoon, but we're able to see that dip. And then we now pick this RF frequency, really about 24.85 gigahertz, and go to work. Okay, so these are some experiments with the microring resonators. These are some of the parametric down conversion experiments. And so if we have 2 frequency bins for signal and idler, we kind of play with 1 phase factor. We can make these nice interference curves with fairly deep contrast. And so the contrast is high enough to really prove that we have, entanglement. It goes beyond sort of what classical local realism theories would predict. We can also, and we've done this more with the SBDC, go up to 3 dimensions. So we have 3 signal-Eidler frequency bin pairs. We put on sort of a nice phase function. We vary this phi parameter, and we can also get interference that starts to sharpen up. Sort of an analogy is the mode-locked laser. As you more and more frequencies, you get sharper and sharper pulses. It's a different process here, but it's sort of the same math. So these start to sharpen up. This is an indicator of an entanglement. We've done a little bit with quantum state tomography here, and so that's consistent as well. And for, you can look at other ways. So you can look for generalized Bell inequalities. And so I won't go into the details here, but with the micro rings, if we have sort of 3 parent frequencies and we use more than one phase modulator sideband harmonic, if you will, we can overlap contributions from 3 Eidler parents, 3 signals. We do this for different phase settings and basically show that we can violate a generalized Bell inequality that was explored some years ago, for example, for time to bin entanglement or time energy entanglement. So we'd like to go up to sort of higher dimensions, but once starting to run out of signal to noise, at this point we still had indium gallium arsenide single photon detectors, and so I think we'll revisit now that we have a pair of SNSPDs, but there's potential to higher dimensionality, so we've shown up to 3. What about briefly about some quote applications? So for example, one of you can make a dispersion measurement, or we can test the sensitivity to dispersion. So we go through 100 meter type of lengths of optical fiber that gives you a quadratic phase function on these different frequency bins. And so we can make these 2 signal 2 Eidler frequency bin entanglement measurements with different signals and Eidlers. And as we do that, we can, for example, look at the phase shift of the interference curve. This is for, I think, maybe the 4th and 5th signal in Eidler. It shifts different amounts for different pairs. We can get dispersion from that. Or we can set it a fixed phase setting and just look at different signal Eidler pairs, and we get a nice spectral interference. And from this, we can derive a dispersion, and it agrees within about 1% of what we expect based on vendor specifications. So probably this is not going to be the commercial way to measure dispersion, but it's kind of interesting so you can do it at very low light level if you like. Another one might be is, we haven't done this yet, but I think we can use high dimensional frequency bin entanglement to sort of radically get better time resolution out of timing jitter limited single photon detectors. Some work that we've done in the past when Joe Lukens was still at Purdue is used a pair of intensity modulators driven by semi-short pulses in front of our coincidence detectors, and with sort of a variable delay between the modulators, sort of a pump probe type of idea, and we're able to push the sort of 350 picosecond resolution, jitter resolution of the detectors down to about 70 picosecond. But it's lossy, it doesn't really scale to much shorter durations. I think if we do something similar with our phase modulators and signal Eidlers, drive these hard to generate a lot of bandwidth, you should be able to get inverse bandwidth type of resolution, and that could be down at the 1 picosecond level based on what we know about making, using electro-optics to make classical frequency combs. And so if you could do that, there might be a lot of interesting things. For example, we heard this morning about seeing around corners based, partly about time resolution. Maybe this could be applied. So we're interested in taking that way. Let me go and talk a little bit about the time frequency hyperentanglement. My student Pulad Amani was giving a poster on this. He's here, was the lead on this. But the idea is, instead of just looking at frequency degrees of freedom, what if we hyperentangle in time and frequency? Now, usually we think of these as Fourier transform variables, but you can work on different time scales. So if you put your time bins far enough apart, so that's longer than the inverse frequency bandwidths involved, it's kind of essentially an independent degree of freedom. And so you can imagine doing hyperencoding in time and frequency. What we'll talk about here is using the 2 degrees of freedom on a single photon to do deterministic, not probabilistic, 2 qubit gates, which we believe is kind of among the first of its kind. The other first of its kind is again from Roberto Marandatti's group, who's also working intensely in this sort of area. They recently published some work where they're also doing time and frequency hyperentanglement on both signals and Eidlers, and talking about essentially showing a three-level cluster state. So, I think this is a very interesting area with a lot of potential. So in our work, what we're doing here is taking light from the microwave resonators. Later on, it'll be from the SPDC that's carved as well. And basically using frequency as a control variable, okay, to control the time degrees of freedom on the on the same photon. And we can use dispersion as well, or just time switching. So for example, part of this setup shows a delayed interferometer with a 1x2 switch. And so we can quickly switch and sort of take sequences of time bins. Now this is pumping with sort of nanoscale pulse, not CW. And we can sort of take the third time bin and run it through a different delay line and end up making it the first time bin, for example. So we've shown that we can make time bin X gates up to 3 dimensions. Actually, some of the other work, I think, will show it up to 16 dimensions in a moment. And then what once we can do that, we can condition that on the frequency degree of freedom. And so we can pick out one frequency, for example, and if we have that frequency, we'll kind of go through the X gate. Otherwise, we'll kind of go around it. So I won't describe that in detail, but it kind of gives you a little bit of sense. We can also use dispersion to put sort of different time shifts, again, depending on frequency. But the result is, if we look in the computational basis, we can make gates. There's a sync gate, which is essentially you take one frequency bin and do an X gate, sort of a cyclic shift of the time bits. Otherwise, you leave it alone. If you look at sort of the 9 states, 3x3 time and frequency, you can see this is a cyclic shift here on one frequency bin. Or in the sum gate, it's basically you take the signal idler bins, you add them modulo dimension. So we can see essentially here we get nothing, here we get one X gate, here we get 2 X gates. And so this is a deterministic, 3x2 qubit gate. Again, we think the first of these together with a group from the IRNS group. We worked recently on trying to scale this, and so here we used an SPD source because we needed some more flexibility on our, basically on our frequency bins. And here's a similar experiment with 16 time bins and 16 frequency bins, and you can sort of see more and more shifts, if you will. I won't go into it, but clearly this is an interesting vehicle for getting to higher dimensions than people can usually get to. The Hilbert space here is 16 by 16 or 256 in a single photon. Harder is to sort of prove the coherence, but we have some examples at the 3x3 level, and here we sort of can start off, for example, with a biphoton comb in 3 dimensions, a single time bin. Using dispersion, which is kind of the first part of the sum gate, we can make a joint spectral intensity like this, where depending on frequency, we're delayed by different times. And after making the sum gate, we can basically use another dispersion module to bring the time bins back together and to overlap. And then we can use these phase modulators in the way I kind of showed before to mix frequency bins, to bring all the time and frequency bins back together and to put on controllable phases, either with another phase modulator for the time bins, which are delayed at this point, or with a pulse shaper, and make more interference curves and can show that the entanglement of formation exceeds somewhere between the 2 and 3 dimension case, and so we can maintain coherence. Okay, so what a potential application. I think Poulad talked about this as well. Here's the idea here is we're growing the sort of Hilbert space we can do with single photons. We still have the problem that it's hard to get lots of photons until we all learn how to make the time multiplexers Paul talked about. So we don't have yet exponential scaling. We have polynomial scaling. And so, probably want to look at sort of near-term quantum information processes where we don't need, 10 to the 8th, Hilbert spaces, but we can take advantage of the ones we have. So one outstanding problem is qubit teleportation, teleporting not qubits, but qubits. So using entanglement as a resource so that state can be prepared at Alice and then sending only classical information and a part of an entangled pair to Bob, transmit the quantum state. It turns out one of not the first, but probably the second teleportation experiment back about 20 years ago actually used 2 degrees of freedom in a single photon, so you could do teleportation with 2 photons, not not 3. They're using polarization momentum. We think this can be transcribed as a sort of going to higher dimensions, working with our time and frequency degrees of freedom. And here an advantage, if we can do this, this is really kind of using potentially chip scale compatible kind of degrees of freedom. So, finally, we're just starting work on this. We don't have results yet, but motivated by the source in silicon nitride being a microring resonator, we would like to bring all these components onto sort of a chip scale. So, for example, pulse shaping elements can be realized using programmable arrays of ring resonator filters that separate wavelengths, put them back together, perhaps with programmable phase shifters in between. Maybe one of the hard parts is the phase modulator, but there's a lot of progress in thin film lithium niobate, for example, recently. We can use more programmable rings to do the separation and to go to off-chip detectors. And so we're exploring 2 routes in a NSF program that started in the last half of last year. Together with my colleague Minghao Chi, we're kind of hoping to see how far we can get in probably silicon nitride together with thin film lithium niobate to sort of really do these things. In parallel, we're exploring silicon photonics solutions via AIM Photonics in a collaboration with AFRL. Mike Fantos spoke here, Stefan Prebel, at RIT, and our friends at Oak Ridge, and we hope to have pieces of wafer to test a little bit sometime this spring to start on that. In addition to going to chip scale, a key point for us is all the discrete components we use are very lossy. And really to scale this at any length, we have to bring the loss way down. And there are challenges. We think potentially we could gain 10 or even 15 dB of loss reduction by going to chip scale. And so we'll see how we can go that. Okay, I won't get into this, but just say there are examples both from our group and others of using arrays of ring resonators for classical purposes. In our case, some of this has been RF arbitrary waveform generation, and wrong way, sorry. And so I'm concluding. Again, thanks to many students and collaborators worked on this. I've mentioned the collaboration from Oak Ridge. We also have some work I didn't talk about here with Misha Brodsky at ARL, kind of in this space, and funding from the National Science Foundation. And here are pictures of sort of current students and, in some cases, recent students who have figured in this work. And I mentioned for any of the integrated photonics stuff at Purdue, Minghao Chi is a close collaborator. So thank you for your attention.
Thank you. Very nice talk. We can take a couple of questions.
Exhaustion. Okay.
Doesn't appear to be any questions. All right, thanks again.
Good. Thank you very much.
No, sorry, Andrew. I do have a question. I was waiting for the microphone.
Oh, yeah, you're kind of you're sort of in a shadow zone there, Paul. Okay.
You made the analogy with the frequency phase shifter with like the unbalanced time bin interferometer in order to measure the interference of the middle term. And normally with that unbalanced interferometer, you get the 3 processes, short, and short, long, and long, short, and you only care about the middle one. But in that case, if you wanted to, you could put a fast switch at the first beam splitter, so you could actually force everything to be in the interfering term. So you could force it so that you didn't have either of the 2 uninteresting extremal pulses. I'm wondering if there's an analogy that you can do in the frequency case.
Yeah, so I may or may not follow your question, but I think you do. There's only some of the different time combinations with the time domain interferometer case that you really show the interference that you want to use. Here it's equally true for our phase modulator sidebands. There's only a subset of them that actually bring you overlap. The other ones aren't useful in the same way. I don't know about fast switching. That'd be good to kind of explore more what you mean, but I will point out when Joe Lukens gives his talk on kind of the manipulating information, they'll describe one scheme that sort of gets around, circumvents the idea of the phase modulation sidebands not all going where you want, where they kind of cause them to sort of come back into the computational space. Thank you.
Any other questions that I missed? Nope. All right, thanks very much.
Thank you.